Do you always start right on time, or 9 a.m. class, that's kind of nasty?
No, I would start time. I try to keep, what is the time?
1 minute after 9?
9:01, okay. So, all right, guys, good morning. And the usual story, laptop shut, etc. Phones up. Thank you. It's my pleasure to, where's Dean?
Hopefully he'll show up.
Okay. So it's my pleasure to introduce, well, I don't need to introduce Dr. Scott Farman, right? Everybody should know him. If you don't know him, shame on you. Now, Scott Farman has been one of the doings of AI. He's also a champion of an endangered language, namely Lisp. He is also kind of famous for his smiley, which is the one thing he doesn't want to be known to be famous for, because he'd rather be famous for his work on AI, which is absolutely brilliant. And of course, the fact that he's made a great number of contributions that you may not even be aware of at this point to neural networks. So we covered quick drops in class. That's Scott's. What you might also not know that is Hinton did much of his early work, his best work here at CNU. And Scott brought him here and was his co-conspirator for some of that work. Right? Yeah,
and he was here for about 8 years.
And
Jeff Hinton.
Also, Steve. So, and one of Scott's contributions, big contributions, is cascade correlations. Now, we've done a lot of work on just understanding what neural networks are, how we're going to train them.
Do you have your, you don't have a laptop, do you have your slides? Okay, I guess we can put them on my machine.
Oh, yeah, do you mind?
Well, the ones you sent?
I sent to him, yeah.
Okay. I didn't see those go by.
Okay, I also have it on flash.
Cascade-Correlation Algorithm. Now, the amazing thing is that Scott first published this work, what, 20 years ago at this point? 30 years ago?
1990.
Yeah, 30 years ago. And we haven't yet seen any work that beats it yet. So we get to hear about it from the author. The other person I'd like to introduce is Dean Albrecht. Do you mind getting us standing up? So he's going to be doing the second or the last quarter of this class. Dean is completing his PhD, but don't get fooled. Dean's a lawyer, and he actually works on legal aspects of machine learning applied to legal problems. And one of the things he picked up on the way was cascade correlations. He's Scott's PhD student. And Dean's going to be talking about some of the stuff he does.
Okay, thank you very much.
Okay, Scott, one thing, so halfway through the class, we're going to stop you for about a couple of minutes, and we will write down a URL on the screen, on the board.
Okay.
That's where people will sign up, because that's our roll call.
No, I don't know how to go back. Okay. As you can see, I'm now a professor emeritus, which means formerly retired. Emeritus is Latin for irrelevant. But I'm still doing research, advising students once in a while, doing a little bit of teaching like here. And the main difference with being retired is that I'm no longer writing funding proposals. The downside is I'm no longer getting paid, but that's okay. So anyway, yeah, I'll be talking about the Cascade-Correlation Algorithm, which is something I cooked up with my then student, Chris Lebiere, who's now faculty in psychology. In 1990, it was one of those things, I had the idea and we were rushing to get some results in time for the NIPS conference deadline, or now it's the NeurIPS conference. We got the one paper out, and then we developed a recurrent version the next year. So I'll be showing you what that's all about. Okay? And these, by the way, those two papers, it's hard for me to go back from the clicker. These two papers are both available online. If you go to my website, there are links to online versions you can download easily, or you can go to the NIPS/NURIPS website. I think they have all the past papers. Anyway, you can just Google it. Okay. So, 28 years ago, I should update that. It's like 30 years ago now. This did a form of deep learning. These algorithms would routinely build useful feature detectors that were 15 or 20 or 30 layers deep. The idea was to run them and build just as much network structure as you need for the problem at hand. Now, as you know, you've all played with neural networks, done some exercises, right? So the first thing you do is you look at the data, see if you've got enough data. And the second thing you do is you guess how many layers and how many units in each layer, if you're going to need convolution, all that stuff. There's not a lot of good theory to tell you exactly how big and how deep a network you're going to need. In fact, there's hardly any good theory at all. And this is why experienced neural net practitioners make the big bucks, because they've got at least, oh, this looks like a problem I did before, and that was 5 layers with 1 million units in each layer, so that's what I'll try in this one. So right now, there's not much theory. There's some experience out there. But people mostly just try whatever worked last time. And sometimes that's the right choice for the new data set. Sometimes it's not. This solves some problems that were considered hard to do at the time, and almost always was 10x and sometimes 100x faster than standard backprop. Some of that was, and faster than backprop with quickprop as well. So you have heard about quickprop, you said. Everything I'll show you ran on a single core 1988 vintage workstation, a whole lot slower than what you guys have on your phones. Let alone your laptops. I spent a lot of nights staying up all night watching the thing. If I'd leave it running and go to bed, it would certainly have been crashed when I got up, and I had to start over. So a lot of late nights just waiting for simple little problems to converge. And of course, we never really attacked the huge data sets that characterize today's deep learning. You know, millions of pictures of beach scenes or kittens or things like that. That just didn't exist. And we certainly didn't have the compute power to do it if it did exist. So what I was really working on is, why is backprop so slow? Really, two problems. That, and is there anything we can do to reduce the amount of guesswork on things like learning rate, on things like the number of layers, number of units, you know, what activation functions to do, and so on. So it seemed to me those were the two big problems, and those are still the two big problems, but on a much larger scale. So I developed this quickprop thing that adjusted the learning rate, okay, and just kind of jumped to the bottom of the curve. It converged a lot faster on many problems. I don't think I ever found a case where it was slower than simple gradient descent backprop, but they're probably out there. In any case, I thought it was still too slow. So what's going on, and I built some little displays to see what was going on, and realized there were a couple of interesting problems. One is what I call moving targets. And I'm not a very mathematical person, so all this stuff was developed basically by thinking about what's the poor unit in the middle of the network somewhere seeing, and what's it trying to do about that? Okay, I tend to personify these things. I shouldn't, but I do. So all the hidden units are being trained at once, and the error signals are coming back, and they're trying to adjust their input weights. And the problem is they're all being trained at once. So the signal they're trying to cancel out, the signal they're trying to do something about, keeps changing because the other ones are learning at the same time. So there's an awful lot of sloshing around rather than just kind of going to an answer and nailing it. Okay, you'll see this, you know, if you build any kind of display and look at your big, gigantic networks training, you'll see this sort of behavior still. And the other thing is what I called the herd effect. There's no central authority that says, you, this unit, number 437, this is your job, you go do it. Okay, what's happening is they're all in the network. You give them all initial random weights. Okay, so they're in different parts of the weight space. And then you start training the network. And they're basically all seeing the same error coming back. Filtered back through the network, it starts looking different. But usually there's a biggest component of the error and then smaller and smaller components. So the poor units are saying, well, okay, there's some error over there. I'm going to go over there and get it. Okay. Rumble. Okay. We'll ignore it. So they all start heading for the same big component of error that they all can see, except the ones off in strange corners of the weight space. But most of them are headed that way. Somebody gets there first and is able to cancel out that error. And all the other units kind of skid to a halt. And where'd it go? I was coming over here to cancel some error, but it's gone now. Oh, well, there's a second component of error over there. Let's go over there. And even the guy who just nailed the first component of the error is now not seeing that anymore. It's gone. So he's going over this way too. Okay, and then it gets uncovered and they'll say, oh, let's go back. Okay, and there's a lot of running back and forth for different components of the error. Okay, now what you would like is some central authority to say, okay, you go get this piece of the error, and then once you get it, stay there. Okay, that's dealt with, you go over there. And it occurred to me one day, sitting on a park bench in Munich, because I had a consulting gig there, what if we added the hidden units one unit at a time? Let each one go do its thing, nail the biggest piece of the error it could, then stay in place and add the next unit. And that basically is the key idea in cascade correlation. So what we would do is start with no hidden units. You've got inputs, you've got trainable output weights. Okay, I've drawn this a little differently than the diagrams you may have seen, and it'll be obvious in a second why I drew it this way. But the inputs come in here. When they get to these red dots, they sum. These are adjustable weights, but they sum a weighted set of these activations, and they go up to the activation function, which is a sigmoid, or in those days it was always a sigmoid. It could be a ReLU or something, and produce an output. Okay? So it's just inputs, adjustable weights, output units, and the outputs. And you can train it up and train it up and train it up, and it gets better and better, and then it reaches a plateau. Now this is basically just a perceptron, and there's this, have you looked at the perceptron stuff at all? So as you know, there are things that provably you cannot do without hidden units. Okay, you can't do a simple XOR, you can't do parity, you can't do anything. With no hidden units, all that the network can do is take the initial weight space, the feature space of the inputs, and cut some sort of a separating plane through it in a high dimensional space. Okay, it can't be a bendy plane, you can't, it's all linear. So all you can do is try to find the best plane in hyperspace. Okay, and there are things you can't solve that way, like exclusive OR. That's the simplest one. Okay, so it learns, reaches a plateau, and then to go any further, it's going to need a hidden unit. So let's put one in. Up. So let's add a hidden unit. Now, what would we like this hidden unit to do? We want it to get some of the residual error and be able to cancel it. Okay, so we train up a hidden unit to match, correlate with, have covariance with largest correlation or covariance possible with the residual error, the remaining error. And once it's all trained up with its input weight, so it's doing something useful, we stick it in the network, we freeze these weights that it just learned, We don't want this guy going anywhere now. He's got a useful job. We want to nail him down. Okay, that's why these are blue. They're frozen. These are still molten. And then you train the output weights. You blend this into the network so far, and it should do a little better. If you can correlate with the residual error, you should be able to adjust the weights and cancel some of it. Okay, does that make sense so far? So this trains, reaches a plateau. There are some problems that need 2 hidden units, not just 1. So this is not going to get any better, but we could add another hidden unit like that. And this takes the inputs, trains itself up to correlate with the residual error, what's left, and be able to cancel some of that. And while we're at it, why don't we look at the output of the first unit as well as just the raw inputs? Okay? You do it again and again and again, and pretty soon, if you've got 30 hidden units, that's a 30 deep network. So each one of these adds a little depth. Now we'll see why that makes a difference in a second. But is that part clear? Okay. So this is just a reiteration of what I was talking about. You start with direct I/O connections only, no hidden units. You train the output layer weights. I use QuickProp for that. If the error is now acceptable, great. Declare victory and go home. A surprising number of problems that people threw at me coming out of industrial data sets were linearly separable. You didn't need any hidden units. They didn't know that. They were using these 3-layer networks, 4-layer networks. And it turned out when you gave it to Cascade Correlation and started the thing up, it just solved it without hidden units. It depends on the input space. It depends on what features you need. But so whenever the error is acceptable, meaning 0 or small enough, you declare victory and go home. Okay? Otherwise, we create 1 new hidden unit, and we do that offline. So you create actually a pool of potential hidden units. Once in a while, one of these, as we're training them, gets stuck. So we create a pool so that some of them will find some useful bit of the error. So we create a pool of candidate units. They're training independently. Each sees the inputs of the network for each training case and the residual error for that training case. And they're adjusting their weights so they maximize their own correlation with the residual error. Okay? So we train. You can guess how long to train or wait until things reach some kind of quiescence, but at some point you say, okay, the candidate units are trained. 5 of them are doing really well. 3 of the 8 are off wandering in the woods somewhere. But let's take the best one and put it into the network now. It's all trained up. Okay, so we call this giving it tenure. As you know, if you spend any time around academia, tenure is what happens to older professors. And when we put this in the network, we freeze its input weights, so he's never going to learn anything again. But now the rest of the network has to listen to him. Okay? And as at a university, the other 7 units that didn't get tenure, they just get massacred and thrown away. They go join Google. So you tenure the winner, add it to the active unit, kill all the other candidates, and you freeze the weights of that unit. It's doing something useful. Don't let it wander off and do something else.
Scott, I'm not sure if you noticed this. If you go back to the previous slide, the figure. Sorry. Yeah. So this is very interesting because when it comes to just training just the output units, that's actually a convex optimization problem.
Yes.
And when it comes to finding just correlations, that too is a convex optimization problem. So you basically collapse something that's a usually non-convex problem to convex optimization.
Right. So we're either training on one phase, we're training to reiterate what you said for the folks at home who are listening, people elsewhere. We're either training the input weights of the candidate units. We might use a pool of 8. I often used 8. There might be 1,000 of them. But the point is they're all independent. Those could be on different machines. And we're not computing anything. We've recorded as we go through the training set what the residual error is for each case. Okay, and we're training against that. So that's very fast. Okay, you do it again and again and again for each individual unit, but it's very fast in each case. Okay, and highly parallelizable. And then when you're training the output units, that's just a perceptron. That's very fast too. It's convex optimization, as Bixia said. Okay? So there's no propagation through multiple layers of the network. There's no vanishing gradients. Okay? There's none of those kind of problems that you get with deep nets when you're trying to train them by backprop. Okay? So it's a bit different game than deep learning, even though the ultimate networks are pretty deep. Okay, retrain the output weights and repeat the cycle until done. Add a unit, train the outputs, add a unit, train the outputs, and so on. Okay, well, does this work? One problem a lot of us used to play with in the old days, this was considered a really big, nasty problem at the time, is two spirals. So you've got two inputs, x and y, and you've got all these training points. So you give it an x and a y input, and you want these ones here, these training points, to be class 1 and the black ones to be class 2, say 1 or 0 output. Okay, so two inputs, one output, but it's a messy thing you're trying to learn. This is like XOR only on steroids. I mean, it's okay. And I trained up a cascade correlation network. It ended up creating 12 units in this case. It can be done with 10. We've gotten solutions that way, and maybe fewer. But it was doing well. It got these guys. Okay, and in fact, it got all the training points right, even though this is a little bit shaggy. Okay, it's not generalizing as smoothly as you might like. In fact, the cases where you got a really good candidate unit and need fewer of them, you got a nice smoother output. Okay, but it's interesting because you can see now what each unit's doing. Here's some stats first. So ran a bunch of cases. Okay, this is many nights of watching the thing trying to converge, because again, these were slow machines. So the state of the art, so-called, is a standard backpropagation network with 2, 5, 5, 5, and 1 units. In other words, 2 inputs, 3 layers of 5 hidden units. Somebody had tried that. And in 20,000 presentations of the entire training set, that's an epic. Is that term still in use? Epic? Okay, passed through the whole training set as an epic. Okay, 20,000 of those, which involved 1 billion link crossings. Okay, and that's a good measure of speed. That's how many multiplies you end up doing, basically. Okay, it's the number of epochs times weights in the network that you have to compute. So 1.1 billion link crossings, it learned it. With quick prop, instead of backprop, it only took 8,000 epochs and a little bit less than half as many actual cycles. With Cascor, it took 1,700 epochs and 20 million. So that's what, better by a factor of 50 than this, and 25 than that or something. Okay, so it's much faster on this particular problem. Okay, and got these nice elegant solutions. And you could see what's going on inside. So here's the output when you just train the output units. And we would scan over the whole input space and see what the receptive field was. Okay, and make a nice diagram. Okay, so without any hidden units, this is the best you can do. What's it doing? It's taking this slice on the outside, which is black, and this slice, which is white, and at least it's getting those right. Once you get into the inside, it's all tangled up and it can't do much. Okay? The first hidden unit, it decides to cut a plane through here. That's correlating with the residual error. And we nail that down, and then we're doing this. Well, what's this doing? It's picking up, there's a lot of white right in here, near the center, and a whole stripe of black right in here, right there. So it's getting a few more cases right. Okay? You all see that? And then it creates a new hidden unit, and it creates one that's like this. Now, before, we didn't have any hidden units, so all it could do is cut a plane through the input space for that unit, the one that's trying to correlate. Now it's a little more complicated space, so when you map it back onto the initial 2D space, it's got a jaggy. That's possible because what it's doing is this and then some of that and then some of that. Okay, it's making use of the fact that it can see that other input unit, that other hidden unit. Okay, so this is the next unit it creates, and now it can do better still. Look, it's getting more cases. And the next unit is really cool because it's getting a little bit of a hook, okay, which is, after all, what you need for this problem. Now it's getting more cases. Now it's got a more hooky hook because it's getting deeper and deeper. It's got a richer space to, and this is always mapping it back to the original 2D space of inputs. But this is the receptive field of the fourth hidden unit, and then the fifth, and then the sixth. You can see it's building up a spiral recognition unit. Nobody told it to do that, but that's what it's doing. Okay, and it's getting better and better, although it's still pretty shaggy here. So let's keep training. Now it's building up something more like that, and it's getting a bunch right here. Better. It's starting to resemble the solution you want. And now it stops building nice hooks somewhere along here, and it starts grabbing patches. It's always symmetrical because the inputs are symmetric and there's nothing to drive it off of there. But so you can't quite see what these are about, but it's getting better and better and better. Okay? So that's pretty cool. You know, people complain about networks being inexplicable. You don't know what's going on inside. Here you can see what's going on inside because each unit has a job, and the job is pretty clean. You can see what's going on. Okay? Questions? So, advantages. No need to guess the size and topology of the network. Yes? Those are outputs that are intermediate between 1 and 0. So I think if it was 0.9, I gave it black and gave it white, and if it was 0.1 or between 0 and 0.1. And then everything in the muddy middle, I just painted gray on that display. Okay, thank you. No need to guess the size and topology and so on of the network in advance. It just builds the network it wants. It can build deep nets with higher order features. And in those days, that was pretty exotic because the biggest nets we could compute were maybe 2 or 3 hidden layers. Okay, nobody was getting 5 or 6 or 8, except me. It's much faster on every problem we tried than backprop or quickprop on a fixed net. It trains just 1 layer of weights at a time, which is what we discussed earlier. It works on smaller training sets, at least in some cases. It's not as data hungry, and we'll see some examples of that in a minute. The old feature detectors are frozen, so subsequent training, maybe on a different set of cases, is not going to cannibalize the old features. We created them for a purpose, they're useful, leave them alone. But what we can do now is add more and more complexity to the training set and do what's called curriculum learning. I don't know if that's been mentioned or covered. But sometimes you can do much better training on some easy cases and then some harder cases and then some harder cases. That's true of people also. Okay. But that's the idea of curriculum learning. You get the thing working on the easy cases, and then you give it some harder stuff, and then some much harder stuff. And the problem with curriculum learning is when you're training the harder stuff, it'll steal things that were important for the easy stuff. So this doesn't do that. Once the detectors are built, they're frozen. And this is good for parallel implementation. Oh, mumble. My tablet and clicker are not friends today. Okay, so, well, you say that's all very nice, but what we really want to do is recognize sequences, not just static. Okay. So in a static network, once it's trained, once you're using it, you put in inputs and the outputs are a function of those inputs. It has no memory of previous cases. So if you're training a sequence, all it's looking at is the thing in the sequence. It knows nothing about the history. So if you want to learn sequential problems, predict the stock market based on past behavior or speech understanding or something, you either need a sliding window so that you have inputs from a lot of previous cases, and that's awkward. It's very inefficient. Or you need some kind of memory in the system. So, well, let's see. Let's look at some, the NIPS deadline for 1991 was looming. Let's try the simplest possible extension that adds some memory to this thing. Or in this case, recurrence. So we're going to use as hidden units, oh, pushed the wrong button, sorry about that. We're going to use, this is the same network we had, the same kind of hidden unit we had before, but we're going to add a tweak. And the tweak is that coming out of the output, there's a one-step delay, and that feeds back into the thing through a trainable self-weight. W sub s is the self-weight. That's how much attention it pays to its previous state. And we train this just like Cascor units. We add them to the network. We freeze them, including the self-weight. And if you look at this, if WS is strongly positive, this thing is a memory cell for 1 bit. The output comes through here. It becomes a positive input, which makes the output go up. And this thing is basically a flip-flop. If it's on, it wants to stay on. If it's off, it wants to stay off. Now, these other inputs can wrestle it into a different state. So usually you want to store something in this flip-flop, but you want it to be able to be overridden by new inputs coming in. Okay, so this is something with some memory, but the memory is not absolutely locked. And if the self-weight is strongly negative, it alternates 1, 0. If it's 1, it comes around here, negative input, now it wants to go to 0, and it just flips back and forth. That's its tendency, and again, the other input weights from previous units and from the raw inputs can override that, basically. They can wrestle the thing into a state other than flipping back and forth every time. Okay, so this is the simplest possible thing I could come up with that had some kind of memory in it. And once we add that, you can do things like learn little simple grammars. So this is another problem that was on everyone's mind back in the day. It's called the Reber grammar. Imagine you have a grammar and you're getting a string of tokens, B's, T's, S's, X's, P's. Those are your inputs. Okay, and in each time step, you're stepping through this grammar. So this is generating legal strings. And what we're going to ask the network to do is you see a string going by and you predict the next token. Sometimes it's indeterminate. So if you see B and then T, the rest either can be S or X, and we made that a 50-50 coin flip. Okay? So this little grammar can generate a lot of legal strings, okay? It can generate B, T, X, S, E, or it can generate B, T, S, 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 X, X, V, V, E. Those are all legal strings. And what we want the network to do is get these inputs one by one, B, P, and then we're asking it to generate the next state. So it's either V or T, so 2 outputs light up. Okay? And so on and so on and so on. So a typical legal string is something like that. Okay, do you see what the game is? Okay. So the state of the art with this thing was something called an Elman net, which had a layer of hidden units, took all the hidden units and put them into memory, and then those were inputs. So there's one time step lag, but you're taking the whole hidden layer and feeding it back into the whole hidden layer. So that's a fixed topology with recurrent units. And with 3 hidden units in one layer, it learned this grammar after seeing 60,000 distinct strings once each. Now, I was a little unhappy with the paper that they published because it showed that they were able to solve it, and they showed their best run and how long that took. We don't know how many million trials it took to get that. Okay. Recurrent cascade correlation. I made a fixed set of 128 training strings and then presented them repeatedly. Okay, so that was enough to give the thing a really good idea what the grammar is. It learned the task building 2 or 3 hidden units. It took 195 epochs, or multiplying by the 128 units, it was 25,000 string presentations. Okay? Set of 128 presented multiple times. And once it had done that, it tested perfectly on all the training cases, and it tested perfectly also on new unseen strings. It had learned the grammar, okay, in a whole lot less time than the Elman net took. So that was kind of nice. Here was a harder problem that people were wrestling with back in the day, and that's the embedded Reber grammar. And this gets into the business of long-term memory. Okay, you've heard maybe LSTMs? Not yet? Well, one of the big problems is, yeah, sure, you can have a little memory of the previous state or two, but what if there's something you need to learn and then remember it for a long time? There needs to be something in the network capable of doing that. Well, it turns out this architecture can do that. So here's a test of that. You get your B and then a T or a P. And then there's the whole Reber grammar, 2 copies of it. Okay, and it generates an intermediate string, like what we just saw. And then at the very end, where it would the original Reber grammar would emit the N token, it has to return either the T or the P that it saw initially. Now what makes this interesting is that while it's doing this, there are T's and P's in there. Okay, so it has to learn that this initial T and P is special, and that's what you got to regurgitate at the end. Okay, so hard problem in those days. The state of the art, again, in Elman net, they tried it, it just couldn't learn the task. Even with 250,000 distinct strings and 15 hidden units, which was a big net in those days, they just couldn't do this. Okay, they burned a lot of cycles trying. So we tried recurrent cascade correlation on this with a fixed set of 256 training strings, presented repeatedly, and then we tested it on 256 different training strings and gave 20 trials of that. On 11 of the 20 runs, perfect performance on the unseen strings. It typically built 5 to 7 hidden units. The worst performance on the others was 20 errors in the entire test set of 256 different strings. So it either absolutely learned the harder problem, or else it kind of learned it, but occasionally would get a wrong output. So 11 of the 20 runs were perfect. And nobody was able to solve this at all on other architectures. So that was kind of cool. So training required an average of 288 epochs and 200,000 string presentations, which is a whole lot less than these state-of-the-art we're trying. Okay? Well, let's try something else. I wonder if we can teach this thing Morse code. Now, I'm an old guy. Morse code was still a thing when I was young. Back before people could send voice over the air, they could send dots and dashes. And not even over the air. This was invented for the telegraph. Okay? So have you all seen Morse code a little bit? You know what the deal is. You got long and short inputs. Okay? And there are a string of dots and dashes represents a letter. And Morse was a smart guy. He said, let's reserve the short strings, like 1 dot and 1 dash will be E and T. Okay, and then 2 will be the next most common letters, and so on and so on. So, and how do we represent this to the recurrent Cascor network? For a dot, we give it a 1 and a 0. Okay, just a single input, 26 outputs, and a thing saying we're at the end of a character. Okay? And how are we going to represent this on the input with only a single input? Well, it's either 1, 0 for a dot or 1, 1, 0 for a dash, which is supposed to be longer. Okay? So the letter V is dot, 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 dash. And if you see 2 zeros in a row, that's the end of the character. It's a little pause. Okay? Everybody see what we're doing? At the start of each letter, we zero out the memory states in the system. So when you see this 0, 0, you say what letter you think it is. That's what we want the network to do. Light up this output saying we're at the end of a character, and that output can be used to zero its internal state, all these recurrent connections. So, and what we're asking it to do is the output should all be 0 except at the end of the letter when it sees the 0, 0, and then it tells you what letter it thinks it saw. So there are, 24 outputs. Plus 1, saying we're at the end of the letter. Okay? So we trained this on the entire, 26 patterns, I'm sorry. Trained this on the entire set of letters repeatedly. And in 10 trials, it learned the task perfectly every time. There were an average of 10.5 hidden units created, and that's pretty cool. Because the longest series of 1s and 0s is more than 10 for a given letter. You don't need a hidden unit for each letter. You don't need a hidden unit for each time step in the presentation. Okay, so it's being quite economical in the way it's coding this. I actually decided I wanted to go back and look and see what those hidden units were doing, and we're in the process of trying to get this thing running again. Some of the code 30 years later doesn't run perfectly. But there was an average of 1,321 epochs through the 26 training patterns, and it nailed the thing. And then it occurred to me curriculum learning was in the air by various different names. But what if instead of learning the whole set at once, we present it a series of lessons. We show it the short letters first and then longer, longer, longer. Okay. So the first we presented it with E's and T's. And say, learn this. And E's, T's, it's 1, 0, 0 at the end, or 1, 1, 0, 0. It just had to get that. So it learned it. And then in increasing sequence length, we set that aside, and then we train it on AIN, DMSU, and these are longer and longer sequences. And we're not repeating the earlier lessons. Start with the easiest training set, learn that, set it aside, next one, next one, next one. Okay? And then finally, just to make sure it all works together, train it on the entire training set. A few times through that. We ran 10 trials. E and T were learned perfectly, usually creating 2 hidden units. Each additional lesson added 1 or 2 hidden units. Okay, we've added another dot or dash to the mix. And the final combination added, to blend it all together, added another 2 or 3 hidden units. So overall, 10 trials, we were averaging about 10 units being created. Okay. And this nailed the problem. And if you look, it required an average of 1,427 epochs passes through the training each set versus 1,321 if you train the whole thing at once. But note that these are much smaller. Sorry about that. These are much smaller epochs. It's just a few letters in each case. Okay, so on the average, this saved about 50% to train it with a lesson plan instead of just, boom, learn this. Okay, so that's kind of cool. And that is, I think, depending very heavily on the fact that we're freezing the units once we create them. Now we've, and right about then, before we could do a lot of follow-up studies, the funding for neural networks in the US went practically to zero. And not being independently wealthy in those days, I wanted to keep getting a paycheck, so I had to go do other things. So there wasn't a lot of follow-on work to this. Papers are out there that got a ton of citations, got me my final promotion to full professor. And, but we didn't do a lot of follow-up work. We were thinking about Cascade Variants, Cascor Variants. There was something called Cascade 2, which we used a different correlation measure. It was more like kind of backpropping into the hidden units instead of looking for a correlation. And that worked better for predicting continuous outputs, it turns out. Now, we didn't have a ton of studies on that, but that seemed to be the case. I mentioned we have this candidate pool. Okay, there are a bunch of units being trained up, all in parallel, to try to correlate with the residual error. You could have different kinds of units in the candidate pool and see who gets the biggest chunk of the error, and that's the one you give tenure to. So you could have Gaussian units, for example, and that would work really nice on radial symmetric things like that two spirals problem. You know, Gaussian unit, right? You could have units that are already pre-built to be edge detectors of some kind. Whatever unit grabs the most error, that's the one who wins. That's the one who gets tenure. One thing we did write, we did put together and play with, was descendant and sibling units. Some people were getting upset that we were generating networks that were 30 layers deep. You know, didn't really need to be that deep. So we said, let's look at half of the things in the candidate pool. We'll look at the previous unit, and half will just look at the previous units. So it's either a sibling or a descendant of the last unit you made. Either it's looking at it or not. And this did indeed lead to shallower networks. It didn't change the performance much. So that was that. So, you know, if for some reason you don't want the networks to get very deep, if you're worried about the delay going through 30 layers, each with one unit, then you can not make the network deeper unless it buys you something. That was the goal here. Could have a mixture of delays and delay types. The single unit delay can't learn everything, it turns out. If you have something with no inputs and it's just you're training it to be a finite state machine and produce some output sequence, it will only produce things that are sort of mod 2 because that's all it can do internally without any inputs. So it can't build a mod 3 counter. Bang, 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 bang. Okay? With the single unit delay, you're not going to be very good at doing things that are time continuous, like speech. So what we could have is a mixture of delays and delay types, or trainable delays. And we never really got into trying all that stuff. You could add multiple units at once to the pool. People say, well, you're training up all these candidate units, and it's pretty wasteful. Why don't you add more than one? Okay. And the trouble is that often the units that are doing well are redundant with one another. So it buys you nothing to add 3 of them. And then there's some units that get stuck off in the corner somewhere. So one thing that's worth trying is adding multiple new units at once from the hidden pool if they don't correlate with each other. They're correlating with different parts of the error. Okay? So that's something that we played with a little bit, but never got enough results to publish. You could even, there's a guy named Tom Schultz at McGill who has been using this Cascor as a model for children learning. They kind of learn and plateau, and then there's a breakthrough. So he thought this was interesting as maybe a way of simulating how kids are learning. Anyway, he came up with something he called knowledge-based cascade correlation. I don't like that name because it's not knowledge-based. But his units were previously learned networks. When he learned a whole network, he could treat that as a candidate unit. Throw it in the pool, see what it can do as a unit. You could have a spiral detector unit, and that could be one of the things, you know. And if anybody ever gives you a spiral problem, this thing's going to nail it. It'll just learn the scale and stretch a little bit, and there it is. So you can play around with all sorts of things in the candidate unit pool. And we certainly haven't explored much of that space. So key ideas. Build just the structure you need. Don't build this huge block of weights and then try to carve the answer out of that huge block of weights. Just build what you need. Seems much more economical, and it is. You can add and train one unit. feature detector at a time, and then freeze it. This eliminates the efficiency due to moving targets and the herd effect. You're only training one unit at a time. It's not being affected by other units trying to learn at the same time. Okay, except the output units, and those don't look at each other. Freezing allows for incremental lesson plan training. And the unit training and selection, all the time goes into training the candidate units, almost all the time. And that's extremely parallelizable because they're not looking at each other. Okay, they can be on 100 different machines. You pass out the data set they're supposed to learn. And we're always looking at the residual error. There's something that the theoretical machine learning people came up with called boosting, which creates a bunch of trained filters or recognizers, and they're all imperfect, but they're imperfect in different ways, so you can keep adding these imperfect ones, and if they're not totally redundant with one another, you do a little better, a little better. This is the same idea. Okay, I didn't prove a lot of convergence theorems and stuff, so I don't get credit for inventing boosting, but there's a boosting. And the big boom in people being interested in boosting came along a few years later. So, I have the old code. I did all my work in Common Lisp. That's a language I helped to invent, so I'm fond of it, and we made sure it would be good for this sort of thing. I had a student named Matt White who translated it all to C. Didn't get any faster. Common Lisp is pretty efficient. But C, of course, was more familiar to more people at that point. And now Lisp is even less used, except by me. So there is a C version, but I'm not very good at C myself. I'm not sure if this thing is up to date enough to just run. There's a body of code. You can find it on my website. Since the AI winter of the 90s, I went off and did some other stuff. I was running a research lab and doing some other things because there was just no money to work on this stuff. And when I came back about the year 2000, the research lab was, the Japanese economy got in trouble and the research lab crashed. It was a Japanese company. When I came back to doing research here at CMU, I said, well, there's still no money for neural nets. There's still no money for common sense learning, which is what I did my PhD thesis on, really was interested in. So why don't I do the common sense thing? I think I can get better results quicker doing that. And there's still no money for this neural net stuff. And then the impeccable timing on my part, then deep learning became this huge thing. But what I'm working on now is this common sense symbolic reasoning thing called SCONE, and that's a whole other talk or series of talks. But I'm interested in collaborating with people who want to play around with this idea, if anybody wants to do a little term project and explore some of this space that I've described that's in large part unexplored. I'm sure there's some papers in there, whether they're publishable or not. You'd have to try them on these damn Kaggle sets now to publish anything. But it'd be interesting to explore some of that space. I think tweaking the memory delay model would allow it to work on time continuous signals, such as speech. And that's something I know Bikshaw's interested in. I think a convolutional version of Cascor is pretty straightforward. There could be units that basically are learning that they're going to be scanned over the whole network. Again, have you had convolutional nets yet? So you can view them either as a unit that gets scanned over the whole space, or as a whole lot of units that are constrained to have the same weights. Okay, each one is doing a center surround or something like that. Okay. So you could cook up these convolutional units, and some units don't cost you too much because they look at one set of features, and other units cost you a hell of a lot because they're going to be scanned over the whole thing. But if that is what cracks the problem, then that's what you want. So this is a whole world to investigate. The hope is that this requires less data and much less computation than the current deep learning models. And I think until we explore that, we won't know, but I think that's an interesting hypothesis. And also, it's more explainable once it's built, because you can see what each unit's doing and so on. So, some current work. Dean is my one PhD student working on some of this stuff, and ported RCC to Python using DINET, and now has a TensorFlow version, which he may or may not feel is stable enough to share. But, and he's using that for, his thesis is really natural language processing applied to the patent system. Patents are this strange foreign language that no human speaks. If you've ever read the text of a patent, it's very different from a story you might read in the New York Times. So it needs a whole different set of NLP tools, and he's looking at the deep learning applied to some of that. And at the end here, he'll be telling us about an idea he's been working on to do the output training a little differently. We have some other ports of this by undergrads and master's students, but none that I think are industrial strength enough for others to use. So there's a problem. People say, oh, okay, I'm going to take the old Cascade correlation code, I'm going to make it work on TensorFlow, and while I'm at it, I'm going to improve it. And in every case, they've improved it so well that it doesn't work anymore. So my recommendation is, if you want to port this to something, try to port it as closely as possible to the original model, get it right, make sure it's got comparable results, and then put in your great new idea. Okay, don't try to do both in one jump, because you'll get lost in the woods. Or at least that's been the experience so far. We have had some things that seem to be working. It's kind of hard to find reported results that we can compare for learning speed. I'd like to do some of the problems that people have reported, but they're always competing on accuracy of things that don't work very well. You know, we're getting 53% on this training set, detecting 53% of the cat pictures on the internet. They always talk about performance and not training speed. And I'd like something that has the same performance, but is much, much faster. And it's hard to prove that, because that's not a reported result. There aren't a lot of data sets. Now, why do people not report the training speed? A, because it's embarrassing. They use supercomputers for a week. But the other thing is, one machine is not comparable to another. What I wish they would report is the link crossing counts, and then we could say, well, on my machine it'll be this, and on this other machine it'll be that. But the number of total multiplies that had to be done, for example. And then we could compare results. Anyway, to get published, you have to say, okay, here's the current state of the art. It's 43%. We just got to 44%. Oh, best paper award. And that's the end of this, and we'll let Dean talk about his new little example.
If you've got any questions for Scott, now's the time while Juan writes down the URL.
Right.
I've got a question that might help, actually.
Okay, great.
Back to slide 11, please.
Slide 11. Probably the easiest way. Slide 11?
Yeah, so just a good question as well, and there's an easy answer, but it might not be obvious because you haven't thought about it very long. But you have the first hidden unit doing something very simple, and maybe bottom right corner hidden unit 6 is able to do something more complex. It's the same activation function in these hidden units. What's the difference exactly? Anyone know? There's a couple of differences, but there's one really significant difference. Why is it able to get a spiral in hidden unit 6, but the first one doesn't have any curvature, it's just this line?
Okay, any hypotheses? Okay, for the people listening elsewhere, the question is, what makes it possible? This is doing the best it can, and it's just cutting the space in half on some hyperplane. And this is doing something much more complicated. So what's going on that enables this to do the more complicated thing? Yes?
That one's operating on different features, essentially, like, because it's operating on hidden unit features rather than the input feature itself. So it may be linear in that space, but it's not linear in the input.
Right. What you're doing really is adding new dimensions to the space. Okay, you start in a 2D space, you're cutting a plane through it. Now with that hidden unit, you're in a 3D space. Now, one of the dimensions is a nonlinear combination of the earlier ones, but it allows this, when you cut through that, it allows this kind of warping behavior, something a little more complicated like that. And you stack a bunch of those, now we're in a 2 input dimensions and 6 hidden unit dimensions, and you're in a much higher dimensional space that when you project back onto the 2-dimensional space, you get something looking like that. At least that's my answer. Do you have one?
I couldn't possibly beat the answer. The algorithm. I sometimes think of it as that the hidden unit that is deeper, like hidden unit 6, obviously has different inputs. It receives different information. It almost looks like you could say it's working on a different data set.
Yeah.
I think that's a good way of looking at it.
So Dean, do you have your slides that you're reading?
I mailed them to you, but
No, I have it in my laptop, I don't know if you brought it
Scott, I
back.
mailed them to you too, so maybe.
Okay, well, let me pull this out so I can move quickly. Okay, and I want to, okay, now I've got to go to my email, if indeed it's there. All right, so the slides from a few days ago,
Yeah,
I actually put them on a memory stick and then forgot to bring it.
but well, I can email them again if you need,
I
but
got
it's the
mine.
same one. Well, you deleted my email?
No, I just have to find it.
Oh, can you search?
Yeah. Well, things are, the iPad is being a little recalcitrant today.
I can tell you the date. I'm sorry, I thought it was,
Okay, you have that?
sorry.
I come
You
prepared.
want to plug in here?
When I say I come prepared, it's,
Okay,
I'm
you got
assuming-
PowerPoint though, right? You could
Yeah.
fire up his.
there you
Oh,
go.
great, thank you.
There we go. Okay, and here's the HDMI.
Yeah. Now, the problem, of course, is that once you do this PowerPoint, what's it trying to combine files for? Okay.
Okay, so we need to get the HDMI going. Do you have an output?
Yes, I do.
And we'll see if the lights come up. Looks promising.
So my laptop has this.
If you go to full, or
Right,
go to
right.
presentation mode, it'll kick in.
But remember that this is a Microsoft Windows
There you go.
machine. Oh, yeah.
Great. thank you.
Okay.
Oh, could you switch the mics? to-
Oh, yeah, sorry.
At least the offline investor live. Thank you.
Yeah, we'll, if we're going to do this for the Super Bowl halftime show, we're going to have to practice it more.
Oh, thank you, thank you.
You want this mic too? You can stick it
Do I
in the
need two mics?
Yeah, well, one's for the room and one's for the
Ah,
folks at home.
okay. Which is which? Two mics, wow,
The first one I gave you is for the external.
okay.
The more important you are, the more mics you have.
Let's see if this works.
Your assignment is very important.
Everyone hear me okay? I can speak arbitrarily loud, so it really doesn't matter.
You can hear.
Come from a loud family, that's where my training comes from. So I just wanted to try and give some intuition for some interesting, well, what I think are interesting ideas, and build on what Scott was doing and what Scott has already told you. And what I really like about Cascor, there's many things I like about Cascor. One of the things I really like is this very simple notion that everyone understands the minute they hear it, which is, well, we're going to take one hidden unit, we're just train it in isolation to do one job. And the one job is correlate with the error. So I've been thinking recently about what that means, and can we broaden it out? Can we make it, can we have different flavors of that idea? So I've come up with 3 versions of error. There's actually an infinite number, so I'll just give 3 flavors. But I wanted to walk through some really simple examples. So this is the simplest possible network. It's at the first stage of Cascor training. We have one output unit, so that dotted line, that dotted circle is the one output unit. And I'm showing you what's going on the inside in 2 steps for a very good reason. We're going to break it down. But basically, it's just say it receives 2 scalar inputs, and the first stage, that first box on the left, you just apply linear weights to it, so you have a pre-activation value. So that P1 is the pre-activation value, and you transform it through some function. Let's say you use the logistic sigmoid function, and you get your output. So again, there's no hidden units, it's just one output unit. We're going to get what I have the y hat, that's my prediction. The network is doing its best to predict what the label is. And I can look at the error. So the way Scott has been talking about error, the traditional form of error in Cascor is the difference between the label y, what you want to predict, and y hat, which is what you did predict in this instance. You also have this other important feature, which is the loss function. And you can have a loss function that's reducing mean squared error or something, but you have this other way of looking at how well your network did, which is your loss function. A little different than just the difference between what you predicted and what you wanted to predict. So that's the setup, and I'm going to refer back to this diagram because we're going to look at different errors at essentially looking at different points in this flow diagram. So, just to recap, we're training hidden units, and the error I view as information on how well the network is doing. And you might say, oh, that's totally obvious. And yeah, I think it is obvious. Error is how well you're doing, and it's a sign of where you need to correct. It's also a sign of what data points you need to correct and what data points you need to correct more. So if the 15th data point in your data set is where you performed terribly, you have a huge error on that 15th data point, that's a signal, that's information that you are given, and you can use appropriately, but it's information that you're given on where you need to improve your performance the most. Okay, so now we can talk about Cascor. So when I want to add the first hidden unit to Cascor, we won't even look at what that hidden unit is. It has an activation function, it correlates, whatever it is. From the output unit's perspective, it's just another signal. It's just another input. So the output unit doesn't even know that it's a hidden unit or it was one of the original network inputs from your data set. It just is another signal that's coming in, right? It's going to weight it accordingly. So from the output unit's perspective, X1, X2, and H is this hidden unit, this new hidden unit that we've just added to the network. They're all identical. So if you view it that way, you say, okay, what is H doing? Well, it's adding to the pre-activation, right? So up there you have this new weight W3 being applied to H. It gets passed through the same way. It'll give me my new error. Hopefully it's lower in some respect, gives me my new loss function. So far, so good? So just to make it concrete, it doesn't really matter, but just to make it concrete, let's say that this is a classification problem. So we'll use logistic activation function for the output unit, and we're going to say that we're going to use binary cross entropy loss. Did we cover? Okay, so you use binary cross entropy loss for the loss function. We're just going to predict whether it's a 1 or 0. So just to give 2 concrete sets of numbers for the data points, 2 data points. So with the logistic sigmoid, it's that S curve. So if you have a pretty strong pre-activation all the way to the right, it's going to be close to 1. If you have a pretty strong negative signal all the way to the left, then it's going to be close to 0. So let's say that the pre-activation for that first data point is 5. It's pretty far to the right. I get an output prediction of 0.99. That's really good. It's essentially perfect. It's very, very close to 1, which is what I want. Now I'll get very little loss because of that. And then I have something that's a decent pre-activation, 1.1. Okay, I get something that's clearly above the 0.5 threshold, but it's not as good as it could be. So I want to increase it. I've got significant loss, right? I have much more loss than the first data point. So again, this is not the interesting part yet, but these are the numbers we're going to use to kind of get a different perspective on what error means or what error could mean. So there's that traditional focus. Traditionally, error in Cascor is look at my prediction, and if my prediction is bad, that's how I measure my error. So that's looking at these numbers here. So if I say the first data point, that red data point, I guessed 0.99 and I wanted to guess 1. So I'm really close. So I'm off by very little. My error from that perspective, this kind of error is very small for the first data point. And for the second data point, the error, I'm off by 0.25. That's one way of looking at the error. But there's other ways. So looking at the error that way, is focusing on kind of this part of the diagram where the output comes out. So there's this other perspective, which is instead of looking at what the output unit produces, look at what was fed to the output unit and say, well, my pre-activation was bad. So from that perspective, the hidden unit that I want to add is going to fix that. It's going to add more pre-activation because that's, in this perspective, that's where the error occurs. So I'm looking at, and I use this funky symbol. Scott didn't like the symbol, but I think I have to make it evocative of error, so it's an E, but I have to use some interesting diacritical so that it's still E. So this E with a, I don't even know what that is, circumflex maybe? Looking at my pre-activation error, the first 5.0, that's pretty close. Let's even say that's as good as I would like it to get. I mean, we know that I could keep increasing pre-activation. I can make it 100, I can make it 1,000. I just get arbitrarily close to 1, but I don't really need to do that. Let's just, for the moment, say, well, 5 is great. If I get 5 for a pre-activation, that means my output's going to be 0.99, which is, let's just say, good enough. But if I have 1.1, I really want to boost that. So I want to predict 1. So when I have 1.1, I'm off by 3.9. I would like to increase that. For that data point, I would like to have 3.9 coming in. There's this other perspective, which is looking at the loss. And there's a reason that you might want to switch among different perspectives. But for the moment, let's just say, well, if I look at the loss, and really that's what you do in backprop, right? You look at the loss, and that's somehow the measure of what you need to correct in the weights. But the loss is looking at this end of it. So if you, again, the first data point, I'm very close to what I want, so it's a really low loss relative to, say, the loss for that other data point. So there's these 3 parts of the diagram that you can focus on for your error. And so, as Scott described, you train a hidden unit, you want to correlate with the error. So one perspective is you can correlate with different flavors of error, different types of error. And why might you want to do that? Why might you want to correlate with one type of error or with another type of error? Well, I'm going to throw out that since the hidden unit has one job, essentially, the hidden unit's job is feed some pre-activation to the output unit. So if the hidden unit does that very well, whatever well means, we'll define. If it does that well, then it's going to correct the error, all kinds of error, loss error, the output error, the pre-activation error well. So for example, we add the hidden unit, and let's just say it correlated perfectly. It correlates perfectly with this kind of error. So the hidden unit on the first data point adds 0. No effect, but we were close anyway, so we're happy with that. And again, assuming the hidden unit did its job perfectly, it outputs a 3.9, it gets weighted by 1, my pre-activation now is 5, and I get another very, very close to 1 result, which is exactly what I wanted. So that's pretty good. So is there a difference between correlating with the pre-activation error or correlating with the regular output error? Oh, there's differences, sure. They look different. They're different signals. But I think it strikes me that it might be easier in some circumstances to say, well, the hidden unit has a job. I'm going to focus on its job and try and make its job as appropriate as possible. So that's maybe true, or maybe true in some circumstances. But a lot of it depends on how well the hidden unit can correlate. And the hidden unit can't correlate arbitrarily well with any signal. So maybe the signals of different pre-activation errors, different errors, maybe it's easier to correlate with one versus the other in different circumstances. The reason, I'll just go back here, the reason that the 2 signals, the pre-activation error coming in and the error coming out of the output unit are different is because you have a nonlinear function in the middle, among other things. So they can't be too similar. Now, I'll just end with this. If I could correlate with the loss function, that in some sense is more appropriate because at the end I really care about the loss. So if I correlate with the loss function, maybe it's not as direct as correlating with the pre-activation error. Again, the hidden unit, all it does is give pre-activation to the output unit. But not all pre-activations are created equal. Some amounts of extra pre-activation one way or the other can lead to more or less loss because the loss function is nonlinear, right? Binary cross entropy. So it might be when you correlate, you don't get to pick and choose where you where you're necessarily going to correlate the best. Don't you want to correlate best with the data points that have the biggest loss, as opposed to just the worst pre-activation? So anyways, this is just throwing out some ideas, different ways of looking at it. I love Cascor because it's so unexplored that I can think about anything I want and not step on anyone's toes, and it's still original. It's still things that no one's done before. I mean, you can look at adding hidden units in different ways by correlating with different types of errors. You can think about, Scott had a lot of examples of different flavors of adding hidden units, sibling training versus descendants training. Can you train outputs? Can you add outputs to Cascor networks? Things like that. So.
One of the things with looking at things your way is perhaps you end up with more easily solvable problems because the optimization might just be easier.
Right. Could be.
You can get rid of nothing answers. Right?
Yeah, exactly.
So another little tweak on this is whether what you're looking for is classification, 1 or 0, or whether it's some sort of continuous output, like predicting the temperature tomorrow, okay, based on whatever crazy inputs you have. One point of view is if you're looking for 1 or 0 output, 0.6 is fine. If 0.5 is the break point, 0.6 is fine. You're in a little danger of crossing over, and this is very close to all the work people have done on maximum marginal learning. Okay, the old perceptrons would get all the training points right, meaning 1 or 0, with a sharp cutoff, and the support vector machines and all the other maximum margin methods. You're trying to, if your training points are like this, you're trying to get the plane so that you're minimizing. Everything's on the right side, but you can still do better maybe in generalization if you get it right through the middle of the empty space, as opposed to up against one of the points. Okay? So, it's a big space of possible error viewpoints to explore. And Dean's got a good idea here, I think. We'll have to figure out if it helps for classification problems where, if you're off by less than 0.5, then that's good enough.
Right. And
you don't really care if it's 0.9 or 1. So, but for the linear prediction problems, it can be very important indeed.
We're kind of running out of time, so I'm sorry to cut these folks off, but maybe we have a minute for questions. Cascor is one of the early and still possibly one of the nicest frameworks we have for actually trying to learn the appropriate architecture for many of these problems. And there are so many openings over here for possible ideas that, at least in terms of course projects and such like, there are possibilities. If you're interested,
Yeah,
I'm going to take the liberty of saying you must get in touch with Scott, who's always been.
We might pass you off to Dean, but the history is kind of interesting. I mean, this got a big burst of citations, created a lot of interest. People threw a lot of industrial data sets at it. When my promotion case came up, I was able to list like 200 people who had applied this to different problems, maybe not published, but had let me know about it. There was somebody who was taking measurements of the foot and trying to translate that into the best shoe size, using a Cascor net. All kinds of crazy measurements of the foot. So ranging from that to stock market prediction and all those things. So it got a big burst of attention, and then there was the kind of deep learning winter for about 10 years. And when things rebooted, people are not paying attention to this at all. Some of the people who were around in the old days remember it, but since I haven't been out there pumping it and pushing, and I'm working on the symbolic stuff now, this remains a pretty virgin set of ideas. There's a lot of unexplored space that could be explored, and so some interesting potential projects here.
Questions? All right, let's thank our speaker. Thank you very much.
Speakers, plural.